All right, so let's begin. Right, two sets of questions we want to look at, generally speaking. Questions on alcohols, questions on carboxylic acids. All right, so the first question. The alcohols form a homologous series. Give three characteristics of a homologous series. Homologous series, they tend to have the same general formula. Alcohols, they all have the same general formula. Each member inside of the homologous series would differ from the other one by a CH2 group. They have similar chemical properties and as well as the same functional group, right? They have similar chemical properties and the same functional group. The physical properties, they vary in a predictable way, right? And they tend to give a trend as you go down the homologous series, right? So things like boiling point and melting point would increase with the number of carbons that are present. All right, so characteristics of a homologous series, they differ by a CH2 group. One, they have similar chemical properties and they have the same functional group. Part B, the following two alcohols are members of a homologous series and they are isomers, right? Now, isomers, they ask you now a question, explain why they are isomers. The reason why they are isomers is because they have the same molecular formula. They have the same molecular formula, but different structural formula, right? What you will not put down is general formula. You will not put down they have the same general formula. You would say they have the same molecular formula, but different structural formula. All right, so next question. Deduce the structural formula of another alcohol, which is also an isomer of these alcohols. All right, now which alcohols are they referring to? They're referring to this alcohol here and this alcohol right here. So in this first one, the OH group is on the first carbon. And in this one, the OH group is also on the first carbon. The difference is on this carbon, we have a CH3 by 2. So we have C2H6 group attached to this carbon here. And we have a CH2 group here. So they're asking you for an isomer of that structure. All right, so what you can do, you can move the location of the OH group from the end to one of the carbons on the inside. Right? So they have 1, 2, 3, 4 carbons present on an OH group. So you move it from the one on the end to the one in the inside. So there's an OH group on the third carbon, and then there's hydrogens all around the rest of the structure. Right? And this here would be an isomer of the alcohol. Now, if we were trying to name the structure, the name of this, check how much carbons we have present. So we have 1, 2, 3, 4 carbons present. So that means the first thing we put down is bute. Bute telling us that we are dealing with 4 carbons. Then we check to see where the OH group is on. The OH group is on the second carbon. So it would be bute and 2 because it's on the second carbon, and all to represent alcohol. Hence the name butane 2-all. Or we could have had a methyl group. Now, a methyl group is a CH3 group. So if we have a methyl group, It means to say that we have a methyl group present on the second carbon. So this is the name here that they put down, and this structure would be CH3 methyl, and that methyl group is on the second carbon in a propan 2-ol structure. So first things first, I'm going to put down the 3 carbons for propanol. 1, 2, 3 carbons. Right, on the second carbon in propanol, we have a OH group, right? But also on the second carbon, we also have a methyl group, which is a CH3 group. So this is what the structure would look like if it was methyl propan 2-ol. 2-methyl, 2 because the methyl group is on the second carbon. Propan, pro because we have 3 carbons present, and 2-ol because the OH group is on the second carbon. All right, next question. Copper 2 oxide can oxidize butanol to liquid X, whose pH is 4. They ask you to give the name of another reagent which can oxidize butanol. Right now, you tell you copper oxide can oxidize butanol. They ask you something else that could oxidize butanol. Butanol is an alcohol. So an alcohol could be oxidized by an oxidizing agent. So potassium manganate 7 or potassium permanganate or potassium dichromate can also act as oxidizing agents, and they can oxidize butanol. Right, so acidified potassium manganate 7, you can put that, or you can put acidified potassium chromate 6. Which homologous series does liquid X belong to? When an alcohol undergoes oxidation, it becomes an acid. Right? Now there's an intermediate step. It could become an aldehyde or a ketone. It's not absolutely necessary for you to know that step at this present level, right? But it goes from an alcohol to aldehyde or a ketone, then to a carboxylic acid, right? But at this level, when oxidation takes place of an alcohol, it generally goes to an acid. Next question. State the formula of liquid X. So you have butanol. So most likely you would have the acid version of the alcohol. So we would most likely get butanoic acid. Right? We would most likely get butanoic acid. So with butanoic acid, basically we would have 1, 2, 3, 4 carbons, C double bond O, OH on the other side, and then hydrogens connected to the rest of the structure. All right, this is what you could have gotten. Right, that would be the formula of the liquid. So that is C4H7OOH. Right, you could have put it out later like that, or you could have said CH3, CH2, CH2, COOH, where you identify each section of it. Right, either way in laying it out would have been correct. Right, but you're dealing with butanoic acid. All right, next question. The alcohol ethanol can be made by fermentation. Yeast is added to aqueous glucose, and the equation below shows us that process, right? C6H12O6, right, gives us 2C2H5OH, which is ethanol, plus carbon dioxide gas. So carbon dioxide gas is given off, and the mixture becomes warm as the reaction is exothermic. So it means to say that more energy is given off than is absorbed. The graph shows how the rate of reaction varies over several days. So as time increases this way, the reaction is increasing, but then at some point, the reaction reaches a high point, and then the reaction begins to decrease. So they ask you, suggest a method of measuring the rate of this reaction. If you want to measure the rate of a reaction, one way in which you can do this is you can measure the volume of gas that is produced. How do we know a gas is produced? From the equation. So we could get something like a syringe that could obtain the gas, right? And as the gas moves into the syringe, it will cause the syringe to move back, and thereby us being able to measure the amount of gas that is produced, and that could help us determine the rate of the reaction. Or we could check time and see how long it takes for the reaction to keep increasing before it starts to decrease, right? So we could either measure volume of the gas produced or measure time taken for the gas to be produced over time. So why does the rate initially increase? One of the reasons why the rate begins to increase is because of the presence, go back to the question, because of the presence of a catalyst. And yeast is that catalyst that allows the reaction to begin to increase. Now the reaction is still happening, but the presence of an enzyme or catalyst speeds up that rate of reaction. So when yeast is added to glucose, the reaction begins to increase, or else the reaction would have continued happening slowly. Now, the next thing we need to note is that when the reaction starts to increase, carbon dioxide is given off, and they tell you the mixture becomes warm. So the increase in the rate of the reaction increases temperature, so which also increases the rate at which the glucose is being converted into ethanol. All right, so it suggests two reasons why the rate eventually decreases. Now, the rate would eventually decrease if there's no more glucose present, or if the concentration of the ethanol becomes so high that it destroys the yeast that is present, right? If there's no more glucose for the yeast to act upon, well, then the rate of the reaction would slow down. And if the concentration of the ethanol that is inside, that is being produced, is so high, it would destroy the yeast or the enzymes that are present. So if the enzymes become destroyed, then the rate will decrease. And if all the glucose is used up, it again would also be decreased. Next question, question 2. The alcohols form a homologous series. Question, give 3 characteristics which all members of a homologous series share. Now, again, another question, they bring this back again. Same general formula, right? Alcohols, they all have the same general formula. They have the same functional group. What is the functional group? OH. Alcohols all have the same functional group, which is the OH group. Next question, next part. There's a common method by which all alcohols can be prepared. They have a similar preparation method. They share the similar chemical properties, and the physical properties, how they vary, they show a trend, and it's very predictable, right? And this would be referring to melting point, boiling point, volatility, viscosity. They would all show a gradual change, because as you move from so as you move from methanol to ethanol to propanol to butanol, more and more carbons are being added to the structure. And in so doing, the physical properties of that compound gradually changes, right? So they asked for 3 characteristics. You didn't have to put down all that I have there. You could only put down 3 as they asked, and that would have been fine. Part 2, give the name of the third member of this series. So you're looking for the third. So the first one is met. The second one is et. The third one is prop. And you add ANOL. So it's supposed to be propanol, but you could have put propan 1-ol, propan 2-ol, or just propanol. Either of them would have been correct, right? You'd be given the third member of the alcohol series. Next one, deduce the molecular formula of the alcohol whose molar mass, Mr, represents that molar mass, whose molar mass is 158, and they say show your working. So we're trying to figure out what alcohol would have a molar mass that is equivalent to 158. So we go back and we ask ourselves, from a periodic table, carbon is 12. Then hydrogen, we know, has a molar mass of 1, and oxygen has a molar mass of 16. So how much times carbon, hydrogen, and oxygen could go into this structure and give us 158? Now, alcohol, as we know, only have 1 OH in it, 1 oxygen. So from the 158, if we were to subtract 16 from that, that would leave us with 142. 142. Right? And of this 142, you have carbons and hydrogens that's supposed to make up that 142. Right? So if we check 10 carbons, we will have 10 by 12, because carbon is 12, which is 120. And if we have 22 hydrogens, right? If we have 22 hydrogens, it will be 22 by 1, which is 22. And I say, but so why 22? If I have 120 and I take that away from 142, I am left with 22. Right? Hence, the number of hydrogens that I would have would be 22. And I know it's only 1 oxygen I will have. So that would leave me with C being 10. I have C10, hydrogen as 22, H 22, and an oxygen, right? But we normally don't write it like this. We would write C10, H21, and put the H next to the oxygen there, right? So hence, we end up with the formula C10, H21, OH. All right, next question. Explain why the following 2 alcohols are isomers. Right? Now, remember, when we speak of isomers, they have the same molecular formula. They have the same number of carbons, hydrogens, and oxygen. They have the same molecular formula. They have the same number of carbons, hydrogens, and oxygens. What is different is their structural arrangement. So they ask to explain why the following two alcohols are isomers. They have the same molecular formula. Same number of carbons, same number of hydrogens and oxygens. Right? That's the reason, that's the main reason why. What is different amongst them? They have different structural arrangement. So where the carbons and the hydrogens are located are different for each structure. So for this structure on this side here, the OH group is on the first carbon. The OH group on this one here is on the central carbon, not the first carbon, the central one. Right? So how they are arranged is different, but they have the same number of carbons, hydrogens, and oxygens. So same molecular formula, different structural arrangement. All right, part C. This question is based on typical reactions of butane 1-ol. When butane 1-ol, CH3, CH2, 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 OH is passed over the catalyst silicon 4 oxide, water is lost. Now, if we remember, if we take an alkene and we add water to it, it gives us an alcohol. So if we have an alcohol and water is given off or water is lost, then basically what that is telling us, simply, that is telling us that we would be getting back the alkene of the alcohol. So if we have an alcohol and water is lost, it means to say that we are getting back the alkene. How so? Water is H2O. H and OH. That gives us water. So if water is lost, it means to say from the alcohol, this is being removed, H2O. So with that being removed now, we would be recreating the alkene. All right, so let's see what they're asking us. Deduce the name and the structure formula of the organic product in this reaction. So the name would be butene or but1ene. Why? Because we have 4 carbons. 1, 2, 3, 4. We have 4 carbons. So the name of the structure could be butene or but1ene if you put the OH on the first carbon. Right, the structural formula, I laid it out here for you. You would have carbon bonded to 2 hydrogens here, 1 hydrogen here, 1 hydrogen there, and then double bonded to carbon. So the OH group that was here, that has been removed. That OH group here that was here, that has been removed, and the double bond has been formed. The double bond has been formed. So with that happening, we have the formation of the alkene, which is butene. All right, so the next part of the question, suggest the name of the ester formed from butanol and ethanoic acid. The name of the ester formed from butanol and ethanoic acid. So what we do, to the alcohol part of it, we add YL. So we end up with butyl and to the acid part, we add OATE. So we take off OIC and we add OATE. So we end up with ethan, ETHAN, OATE. All right. So we end up with butyl ethanoate. That should be the name of the ester that is formed when butanol and ethanoic acid reacts with each other. All right. So they tell you butane-1-ol is oxidized by acidified potassium manganate. Deduce the name and the structural formula of the organic product in this reaction. If the alcohol undergoes oxidation, this here was not what we're going to get. If it undergoes oxidation, instead of butanol, we will have the acid formed. When the alcohol undergoes oxidation, when the alcohol undergoes oxidation, and this sign represents oxidation, right, it produces the acid. When the alcohol undergoes oxidation, it produces the acid. So what we will have is the acid of the alcohol. What is the alcohol? Butane-1-ol. So the acid will be butanoic acid. So the name that should be here is butanoic acid, right? Butanoic acid. Butanoic acid. ACID. Right? Not this name here. Butyl ethanoate. That is for this here. That answer should be there. Right? The name of the structure that you will get here for part 3 is butanoic acid. Why? When the alcohol undergoes oxidation, it always gives you the acid. When the alcohol undergoes oxidation, it always produces for you that acid. Right? The structural formula for butanoic acid, but meaning we have 4 carbons. We put down the acid group, which is C double bond O, OH. This acid group we have here. And we have hydrogens all around the rest of the carbons, so that each carbon have 4 bonds. Next question. Alcohols can be made by fermentation or from petroleum. Alcohols can be made 2 ways, by fermentation or from petroleum. Part A, ethanol can be made by the fermentation of glucose. So they're using one process, which is the fermentation of glucose. They give you the equation, glucose, yeast is added to it, yeast is an enzyme, and it produces for you ethanol, C2H5OH, plus carbon dioxide gas. And they tell you that this reaction is an exothermic reaction. When we speak of exothermic, it means that more energy is being given off than absorbed in. More energy is being given off than absorbed in. So yeast are living cells, single cell fungi, which ferment glucose by anaerobic respiration. Now in biology, anaerobic only means the absence of oxygen. Anaerobic is the absence of oxygen. So this reaction is catalyzed by enzymes from the yeast. So in order for this reaction to take place, yeast is needed, and it gives us the product that we want. So they ask you, what is meant by the term respiration? So when we speak of respiration, we can say the following. Living organisms produces or releases or could gain energy, and they use that energy to survive. The energy can be used to move from place to place. But when we respire, I'm not talking about inhaling and exhaling. I'm talking about your body using energy to perform tasks, right? So living organisms, right? So for example, yeast cells, plant cells, animal cells, right? They produce or release or gain or obtain energy, right? And this is exothermic energy, right? Energy that can be given off, right? And they obtain that energy from food, right? The food you eat, carbohydrates, sugars, and so on. And they use that energy to survive, right? In the process, respiration takes please. Next part of the question, what does anaerobic mean? Anaerobic means in the absence of oxygen. Name the products formed from respiration in the presence of oxygen. When oxygen is present, and mind you, this is where chemistry and biology overlap, right? In the presence of oxygen, we produce what is called ATP, adenosine triphosphate, right? And this here is basically the chemical energy that our body produces, right? The chemical energy that we can produce so that our cells can operate, they can move, the muscles can operate. Right? So they ask you what's the name of the products that are formed? Carbon dioxide, water, and energy. Remember, respiration is the reverse of photosynthesis. Respiration is the reverse of photosynthesis. So how do we get photosynthesis? Carbon dioxide plus water in the presence of light and chlorophyll would give us glucose. The reverse is happening when we respire. In respiration, the glucose is being broken down to carbon dioxide and water, and energy is being given off. So it's the reverse of respiration. If oxygen is present, the reverse process will take place. Next part of the question. What are enzymes? Enzymes are biological catalysts. That's what enzymes are. Enzymes are biological catalysts, or enzymes are proteins and they are catalysts. What do? They alter the rate of a reaction. So they say, next question, suggest a method of measuring the rate of this reaction. Because carbon dioxide, again, can be produced, then the rate of this reaction, we can check to see how long it takes for lime water to turn milky, because lime water can test the presence of carbon dioxide gas. So when lime water turns milky, we know that only carbon dioxide is present and is being produced. We can check the time taken for that to occur. Now, the time taken for bubbling to stop. Carbon dioxide normally gives off a gas, fizzing. When you have your soft drink, the fizz that you get in the soft drink is from carbon dioxide gas. It's a carbonate, right? So if you have carbonates present, carbon dioxide gas is being evolved. So effervescence, you can check the time taken for the bubbles to start and stop, and you can check that. You could also count the number of bubbles if you wanted to, or you could measure the change in temperature, and you could check the time taken for it to start and how long it takes to end. You could measure again carbon dioxide gas with time if you want to. So there are many different ways by which you could go about measuring the rate of this reaction if you wanted to. I've listed some here for you, but you don't have to put down all of them. All right, so next question. The following observations were noted. When a small amount of yeast was added to the aqueous glucose, the reaction started and the solution went slightly cloudy. So once it goes slightly cloudy, we know that carbon dioxide gas is being produced, right? Because carbon dioxide gas helps to turn lime water cloudy. So the reaction rate increases and the solution becomes cloudier and warmer. After a while, the reaction rate decreases and eventually stops, leaving a 14% solution of ethanol in water. The question is, why did the reaction rate increase? The reason why the reaction rate increased is because small amounts of yeast was added to glucose dissolved in water. It's aqueous, right? When that happens, then the temperature increases with increasing temperature, heat increases, it gets warmer, there's a higher temperature, more energy is being given out and absorbed, and that's because we added more and more yeast to our aqueous solution of glucose. As the yeast increased, the rate of the reaction increased. All right, so just an explanation for the increase in cloudiness of the solution. The more yeast that is present, the more alcohol is going to be produced. The more alcohol is produced, the more carbon dioxide is produced, right? So therefore, the increase in cloudiness it is, what's the word? It increases at the same rate at which the ethanol would be increasing. So when ethanol increases, the carbon dioxide, that gas that is produced, is also increasing. So thereby increasing the cloudiness of the solution that is being formed. Right? So when we're trying to explain the cloudiness, this is in relation to the carbon dioxide that is being produced. As the yeast we add, as more and more yeast that is added, more and more alcohol is produced. All right? More and more alcohol is produced. So that also means more and more carbon dioxide would also be produced. Give two reasons why the fermentation stopped. Well, the fermentation could stop if the yeast cell dies and we don't have the yeast anymore. If the enzyme becomes denatured, meaning to say that the active site of the enzyme don't function anymore, or it loses its ability to function, right? Or all the glucose has reacted and there's no more glucose left to react. All these things can stop the process or make the process reach an end. Next question. One use of ethanol is in alcoholic drinks. Give two other uses of ethanol. Ethanol is used as in hand sanitizers, as you will know. It's used to kill bacteria. It's used as a sterilizer. It's used in spirit lamps, in thermometers, in making vinegar, in making ethanoic acid, in essence and flavoring, to preserve foods, and to have many, many other uses of ethanol. But those are just some they asked to list two, so you could have listed any two. Next question. Alcohol can be made from petroleum by the following sequence of reactions. Alkanes from petroleum gives you alkenes, so that would be cracking, it would undergo cracking, and then alkenes in the presence of steam can give us alcohol. They ask you to describe the manufacture of ethanol from hexane. Include in your description an equation and the type of reaction for each of the steps. So hexane undergoes catalytic cracking to obtain ethene and butane. So C6H14, which is our alkane, undergoes cracking and it gives us the alkene, ethene, and butane. How we know that we're correct? We started off with 6 carbons. We still have 6 carbons. 4 and 2 is 6. We have started off with 14 hydrogens. We still have 14 hydrogens. We have 10 and we have 4. So in total, we still have 6 carbons and 14 hydrogens. Now, the next step of the process is the hydration of ethene by adding steam or water vapor to the alkene that gives us the alcohol. So the hydration of ethene or the addition of steam to it then helps produce the alcohol, ethanol. So C2H4 plus water, and of course this would be a gas, water vapor in terms of steam, that then produces the alcohol. So alkanes to alkenes, that is cracking in the presence of a catalyst, and alkenes to alcohol, that's hydration by adding C. Next question. Esters, polyesters, and fats all contain the ester linkage. Now, just to remind you what the ester linkage, C double bond O. O. When we see this, we know that an ester is present. C double bond OO tells us that the ester is present. So esters can be made from alcohols and carboxylic acids. So when alcohols and acids react, it gives us an ester and water. When alcohols and acids react, it gives us an ester and water. So for example, the ester ethyl ethanoate can be made from the following reaction. This here is the acid, and this here is the alcohol. So the alcohol plus the acid, that gives us the ester. That gives us the ester and water. So an alcohol plus an acid gives us ester plus water. So the question asks us now to name the carboxylic acid and the alcohol from which the following ester could be made. So here we have an ester. This is our ester here. How do we know it's an ester? Because of this functional group, C double bond O, O, right? That tells us that we're dealing with an ester. So one part would be to the alcohol, and the next part would be to the acid. So CH3O, hydrogen is going to be added back here, because what happens is that this bond is going to break, and water is going to be added across that bond. So hydrogen is added to the oxygen here. When this splits, hydrogen is added to the oxygen, and we end up with an alcohol. So we have HOCH3. And this is one structure, right? Which is our methanol. And then on the next side, I'll have this structure where added to it, I will have the other part of the water, which is the OH group, coming and attach itself here to help form the acid. So I will have 1, 2, 3, 4 butanoic acid as the name of the acid, and methanol as the name of the alcohol. Hence the names of the acid and the alcohol that would give you this ester is butanoic acid as well as methanol. All right, next question. 6.0 grams of ethanoic acid has a molar mass of 60, and that was reacted with 5.5 grams of ethanol, which has a molar mass of 46. Determine which is the limiting reagent and the maximum yield of ethyl ethanoate, which has a molar mass of 88. All right, so in order for us to find out which is the limiting reagent, we need to find out which one has the least amount of moles. In order to find the number of moles, now I would not have done moles with you. The formula to find moles is mass divided by molar mass. The mass given for ethanol, for ethanoic acid, is 6 grams, and the molar mass given is 60. So what you do, you take 6 and you divide it by 60, mass divided by molar mass, and that will give us the number of moles. And then you do the same thing for the ethanol. Moles is equal to mass over molar mass. The mass given is 5.5 grams. The molar mass is 46. So you take 5.5 and you divide it by 46, and that will give you the number of moles that has been produced. So we check the 2 moles and we see which one is the least number of moles, and that is our limiting reagent, right? The one with the least number of moles is our limiting reagent. In this case, it will be 0.1, which is the ethanoic acid. All right, so the next thing now They tell us we need to find the number of moles of the ethyl ethanoate that is formed. Right now, with the ethanoic acid also being the limiting reagent, there's a 1-to-1 ratio of the limiting reagent to the ester that is formed. So thus, or this means to say that the same number of moles of the acid would equal to the number of moles of the ethyl ethanoate, which is the ester. The same number of moles of the acid would equal to the same number of moles in the ester. So therefore, we can now take this here and find the mass of ethyl ethanoate that is produced. The formula to find mass is moles multiplied by molar mass. So to find moles, we divide the moles by the molar mass by the mass, and that gives us moles. To find mass, we multiply moles by molar mass, and that gives us the mass. The molar mass from the question is 88, and the number of moles, because of the 1-to-1 ratio, the number of moles is 0.1. And 88 multiplied by 0.1 gives us 8.8 grams of ethyl ethanoate being produced. All right, so this is just to actually lay it out so you can see it. The ethanol, the alcohol reacting with the acid, the ethanoic acid, it produces for us ethyl ethanoate plus water. Water is the H2O on this side here. This here is your water. And on this side here, this is the ester being formed because there's the ester linkage, C11OO. That tells us that this is an ester on this side and water is produced on that side. All right. Next question. The following two monomers can form a polyester. Right? Now remember, when we're talking about polymers and polyesters, poly means many. So polyester means we have many ester units. Polyester, there are many ester units. They say draw the structural formula of this polyester. Include two ester linkages. All right? Include two ester linkages inside of it. So in order for an ester polyester to be formed, we need a dicarboxylic acid and a dialcohol or a diol. Right? A diacid and a diol. Why is it a diacid? Because we have two acid groups. We have one on that side and we have one on this side. And why is it a diol? Because we have two OH groups, one on this side and one on that side. Now, what's going to happen? Water is going to be lost as these structures come together, right? These structures merge and water is lost. Water is lost from the two structures and they merge and come together. Water is lost. So this one should be shaded. All right, and this one's supposed to be lined. All right, so what this translates to, all right, so this structure here is the same structure in the middle here, and this structure here is that structure in the middle there. This translates to water being removed. So this structure is being repeated here for this part up to there, but water has been removed and the oxygen from there comes and binds here. And the rest of the structure continues, but again, the H and OH from the next presiding structure is removed again and a second unit is repeated. So I've done the unit here once. You have one stroked and one fully shaded, and the next one stroked and the next one fully shaded to show that ester linkage. There are two of the ester linkages there. We have one that can be clearly seen, and we have a second one that can be clearly seen. We have a third one that you can clearly see. Right? So you can clearly see that there's at least two ester linkages inside of this. I just put more than two so you can see it as clear as possible. Ester linkage, ester linkage, ester linkage. They are linked together because the dicarboxylic acid and the dialcohol, which is the diol, have come together and given up what is called the water molecule so that they can merge together. All right, so this is condensation polymerization because the diacid, and again, this is another way I try to represent it for you guys. If you look again, you're still seeing the acid group on either side, the acid group, and the R now takes the place of what was the box just now. All right, and water, H2O, water is being removed. Water is being removed. And over on the next side, this R group here takes the place of the box I was there before. And again, water is being removed. So they come and bind together, and we have the formation of that ester linkage when they bind together. All right, and that ester linkage helps us to form many ester linkages, which are referred to as polyesters. And we have the formation of what we call a polyester. All right, so moving along. Fats and vegetable oils are esters. The formula of 2 examples of natural esters are given below. So they have 2 esters. You have one over on this side here, ester 1, and on this side here we have ester 2. Okay. So one ester is saturated and the other is unsaturated. Okay, describe a test to distinguish between the 2 of them. Now, when we talk about something being saturated or unsaturated, we are talking about the presence of double or single bonds. Presence of double bonds or single bonds. So the test, in order for us to determine whether it's saturated or unsaturated, we can use the bromine water test, where we add bromine water to the samples and see if the bromine water goes colorless. Right? If it goes colorless, that means a double bond is present. Right? If it does not go colorless, then double bonds are absent. If it don't go colorless. So, the result with the unsaturated ester, it means that it will go colorless because a double bond is present and can be broken. The result with the saturated ester, the color remains the same because there would only be single bonds inside of the chain. Now, what am I talking about? This chain here that is added on to this structure. Right? This long chain here that is added on to the structure. So they tell you one is saturated and one is unsaturated. Right? Now, you don't have to go through the whole structure to try and figure it all out, but that is the basic reasoning behind it. Right now, to tell you, deduce which one of the above esters is unsaturated. Now they ask you to give a reason for your choice. So the one that is unsaturated is ester 1. And I'll explain to you why that this one is unsaturated. Now, when we talk about alkyl groups, an alkyl group is a CnH2n plus 1 group. So CH3 is methyl. C2H5 is ethyl. C3H7 is propyl. C4H9 is butyl, right? So those alkyl groups would tell us whether or not it is unsaturated because that alkyl group is supposed to correspond to this portion of the chain. So if we were to check this portion of the chain to see if it follows that pattern, then from that we can determine whether ester 1 is unsaturated or whether ester 2 is unsaturated. All right, so let's go and do that right now. So if I were to take C17, H2 by 17, and then this is supposed to add 1 plus 1. This is supposed to give us how much hydrogen is supposed to be present with this structure. And that will in turn tell us whether there's a double bond present or absent. So 17 by 2 is 34 plus 1 is 35. So C17H35 will only have single bonds. C17H35 will only have single bonds. So that means to say that this ester here is a saturated ester because there are no double bonds present inside of that structure. However, C17H33 means to say that there are some double bonds inside of here, is because 2 of the hydrogens are not present, right? So there's a double bond present because 2 hydrogens has been removed, C17H33. While ester 2, C17H35, follows the formula CnH2n plus 1. Right? So which one is unsaturated? Ester 1 is unsaturated. And the reason why is because there are double bonds present in that structure, and it does not follow the general formula CnH2n plus 1, which is that of a alkane. All right. Part 3, both esters are hydrolyzed by boiling with aqueous sodium hydroxide. What type of compounds are formed? Basically, a soap will be formed, right? Coming down to the end of class today, I would play some videos with you about what is saponification and the making of soap, so that this year would make a little more sense, right? But just for the interest of answering the question, a soap will be formed as well as an alcohol. Right? The salt of the acid, which is the carboxylate or the sodium carboxylate, salt of it is formed, but the alcohol is also formed with it. So there are 2 products that we get from it, the salt and the acid. The ester linkage, question 5. The ester linkage showing all the bonds is drawn below. C double bond O, O. Or more simply, as it can be written as COO, and they show you there. Give the structural formula of the ester ethyl ethanoate. Right, the structural formula of ethyl ethanoate. This here is the structure. This here is from the alcohol part of it. So this would have been ethanol. Et because there are 2 carbons, and there was a OH present here. The H was removed when water was removed. And on the other side here, this is our acid, which was ethanoic acid. Right, ethanoic acid. And OH was removed from the structure. So therefore, that's how they came up with ethyl, because YL was added to the alcohol. And anoate, the OIC from the acid was removed and OATE was added. So the structural formula for ethyl ethanoate is this structure given here. Deduce the name of the ester formed from methanoic acid and butanol. Again, the butanol, ANO, the anol is going to be removed and YL is going to be added. And for the anoic acid, OIC is going to be removed and OATE is going to be added. So we end up with methanoate and butyl. So the name of the ester would be butyl methanoate. All right, next question. Which group of naturally occurring compounds contain the ester linkage? Which group of naturally occurring compounds contain the ester linkage? Right? Well, naturally occurring compounds, we're talking about compounds that exist naturally in nature, right? We as man didn't try to reproduce it or create it. It was already there and existed in nature, right? The answer to that, your fats, your vegetable oils, your triglycerides, your lipids, high density lipoproteins, low density lipoproteins, all these substances, they naturally occur um, in life, and they contain the ester linkage. What is the ester linkage? C double bond O bonded to another oxygen. All right, C double bond O bonded to another oxygen. So draw the structural formula of the polyester formed from the following monomers. Now, if you look at it closely, at first it's going to look as if it is Greek. But if you take a closer look at it, you realize that it's not. There's a C double bond OOH here, which means to say it's a carboxylic acid. And there's also C double bond OOH here. So we have a diacid on one side. And on the next side, we have a OH on this side here. And we have a OH on that side over there. So we have a diacid and a diol. A diacid and a diol. So if you were trying to draw the structural formula of the polyester that is formed from this, again, OH is going to be removed from here and hydrogen is going to be lost from there. So this structure, water is going to be removed, and then they would come and they would bind together. So we'll end up with a structure. So this C6H4, this structure here, is added there. All right, and then we have the C double bond O from this is this structure here. The oxygen from this structure is there. The CH2 is this box here. And the oxygen from here is that structure there. Hydrogen is going to be lost. And the OH from the next structure is going to be lost. And this process is going to be repeated and repeated and repeated and repeated and repeated. So this here is the structure of our polyester. All right, that is our polyester that has been formed. And the monomers would have been this here and that there. All right, next question. Esters can be used as solvents in chromatography. The following shows a chromatogram of plant acids. Now, if you watch, there are 10 blocks here, another 10 blocks there, another 10 blocks here, another 10 blocks there, another 10 blocks here. All right? So this, if we put in a scale, 10, 20, 30, 40, 50, and so on. All right? And we have our samples. They have a sample. They have one sample here. And they have a next sample that they put there. So they have two samples. The sample move all the way up to here. So this is like 11. And the sample move all the way up to this. So that's like 21 to 22 or 23 somewhere there. Okay, no problem. All right, now the solvent front is the distance moved by the liquid that this chromatogram was placed in. So this would have been the chromatogram, and this would have been a beaker with a solution in it. And what they would have done is they would have placed the sample on the dot right here, and then they would have dipped this into the water. But this sample, this line, does not fall below the base of the water, right? And then the substance travels up the chromatogram just like it did here. It traveled up the chromatogram, right? It traveled up the chromatogram. All right, so let's go to the question now. An ester was used as the solvent and the chromatogram was sprayed with bromomethyl blue. Anytime they're spraying with bromomethyl blue is because the sample is colorless and they cannot see it. So therefore they spray it with an indicator to help make the sample become visible, right? So why was it necessary to spray the chromatogram? That is to make the invisible color, or the invisible spots, make it color. So give it color so that we can see it clearly. Right, the next part of the question, say explain what is meant by the RF value of a sample. The RF value is the retention factor. RF stands for retention factor. And in calculating the retention factor, that's very simple. It's basically taking the distance moved by the sample and dividing it by the distance moved by the solvent front. Taking the distance moved by the sample and dividing it by the distance moved by the solvent front. The solvent front moved 10, 20, 30, 40, 50. So the solvent front moved 50 of these blocks, while sample 1 moved about 10 and 1 is 11, and sample 2 moved 10, 11, 12, sorry, 10, 20, 1, 2, 3. Move about 23. All right? So the distance traveled by the sample, which would be sample 1 and sample 2, over the distance traveled by the solvent front. So in essence, it would have been 11 over 50 for the first sample, if I wanted to calculate it, and 23 over 50 for the second sample. And the answer from this tells me what the retention factor of the sample is. The answer from that tells me what the retention factor of the samples are. So then they ask you, calculate the retention factor value of the two samples and use the data in the table to identify the plant acids. So from this, they're trying to figure out, okay, which of these plant acids are present on our sample? Which of them are present? Right, so again, we just do the same thing what I just did. We take the 11 divided by 50, and that will give us the answer, 0.22. So this is possibly one of the acids present. And we take 23 divided by 50, it gives us 0.46. 0.46, this is possibly the next acid present. And the first sample is tartaric acid, and the second one is malic acid. All right. So far, I trust that that's making some kind of sense. I know it's going to be a lot for you guys to take in, right? That's why I have tried to answer all the questions beforehand, so we'll be able to get through a lot more questions, right? But just keep following, and if you don't understand, please send me a message in the chat so I can address what you're not understanding or what you're not following. All right, please don't let me reach to the end and then you tell me you don't understand. That way I could address it right away, and instead of going all the way to the end before you don't understand, you can let me know so we can fix it one time. All right, so we're going to do some multiple choice and try to incorporate the information again and see how we get by with that. So question 1, ethene forms an addition polymer as shown below. It forms an addition polymer. So how we know it's an addition polymer is because the double bond is being broken and hydrogen is being added across the double bond. Which term describes this polymer? Which term describes this polymer? Is this polymer a saturated compound called polyethane, a saturated compound called polyethene, an unsaturated compound called polyethene, or unsaturated compound called polyethene? 30 seconds, guys. Let's see who has an answer for me. The first proposed answer so far is C. Let me see if anybody else support that. Somebody else says C. Let's see, let's see. Anybody else have any answers to contribute? All right, so let's see if that answer was correct. When we say something is saturated, it means to say that there are only single bonds present. They're asking you about the polymer that is formed. Which term describes the polymer? So this polymer over here that is formed is what they're asking you. So if we check saturated, you say A now. All right, so somebody changed the answer from C to A. So when we say saturated, it means to say only single bonds are present. Now there is an exception to the rule when naming polymers, right? When we name in polymers, the polymer takes the name of the monomer, but yet still have single bonds. The polymer takes the name of the monomer, but yet still it would have single bonds. So the name of this here is supposed to be polyethylene, E-N-E, because it was derived from the alkene, right? But it takes the name of the ethene or the alkene, even though there are only single bonds present inside of them. Even though there are only single bonds present, as you can see there. Right? So the name, this compound is actually a saturated compound called polyethylene. Saturated because there are only single bonds present inside of this structure here. So the answer is B as in boy, not A as in apple. Right? Now the reason why it's not A is because it's taking the name of the alkene that it was formed from. I know that there are only single bonds present in the polymer that we see in there, only single bonds. And according to what we've learned thus far, it should be an alkane. But it's not an alkane in that it has the name of the alkene because the double bond from the alkene is broken and that unit is repeated over and over and over. So the answer to this question, in my opinion, is B as in boy. Yes, 1B as in boy. All right, question 2. Which statement about carboxylic acids is not correct? Which statement about carboxylic acids is not correct? So let's see. Aqueous ethanoic acid has a pH below 7. It's an acid. All acids will have a pH below 7. So that is correct. They contain the functional group COOH. Yes, they have the functional group C double bond O, OH. That is correct. They produce carbon dioxide when they react with a metal carbonate. An acid plus a metal carbonate produces carbon dioxide. That is correct. Methyl orange, which is an indicator, turns yellow in aqueous ethanoic acid. No, it does not turn orange. It actually turns red. Right? So instead of, sorry, it doesn't turn yellow. It goes red. This color here should have been red. Methyl orange turns red, not yellow. So the answer is D as in dog. All right. Okay, so next question. What are the properties of a dilute solution of ethanoic acid? All right. So they're odorless, no. Colorless, yes, they're colorless. They have a pungent smell, Yes, ethanoic acid has a pungent smell. So it should be, they have a pungent smell, but they don't have a color. So they can appear colorless, but with a pungent smell. The answer should be C as in cat, I believe. Right? So they ask you, what are the properties of a dilute solution of ethanoic acid? Acid gives off a pungent smell. You don't want to smell acids or bases because they have a strong scent, right? What you would do is you would waft the scent to your nose rather than sniffing it in as if you're sniffing coke or something, right? So the answer should be C as in cat. They have a pungent smell, but they are colorless. All right, next question. Question 4. Which statements are correct for ethanoic acid? So I'm going to give you 30 seconds, guys. Let me see if you can come up with the answer for this one. Which statements are correct for ethanoic acid? Right? So this should be 1, 2, and 4 here as the answer. 1 and 3, 1 and 2, 2, 3, and 4. All right, so yes, which ones are correct? Let me hear what you have to say. So the first thing, it contains a carbon oxygen double bond. Right? And that is correct. They have a carbon oxygen double bond. It contains 2 carbon atoms. Yes, they must have at least 2 carbon atoms. Ethanoic acid. All right. All right. It decolorizes bromine water. No, and the acid wouldn't decolorize the bromine water. And it contains a OH group. Yes, it will have a OH group present because it's an acid. You'll have C double bond O, and there's a OH present inside of the structure. So the answer should be C as in cat. Question 5. The structure of a compound Y is shown below. So they show you the structure, carbon, and you have C double bond O, OH. We know that is a acid that we're dealing with because we have C double bond O, OH. All right, so which row describes some of the physical properties of Y? It's colorless. The acid would be colorless, yes. So it could be either C or D. They have a characteristic smell, yes. It could be either C or D. They dissolve in water, yes. They would dissolve in water. So that leaves us with D as the answer. So the answer to this question is D as in dog. All right, question 6. Which statement describes the compound shown below? All right, which statement describes the compound shown below? Again, we look for the functional group. First thing, we have C double bond O, OH. So we know we're dealing with an acid. So is it a colorless flammable gas? It is colorless, but the acid wouldn't flame up like an alcohol. It is a liquid which decolorizes bromine water. The alcohol would actually not be, sorry, the acid will not be a gas, it will be liquid. Is a liquid which decolorizes bromine water? No, it would not decolorize bromine water. It is a liquid with a characteristic smell. Yes, it is a liquid and it has a pungent scent. It is formed when ethane reacts with steam. No, when alkane reacts with steam, that will not give you. If an alkene, if this was an alcohol undergoing oxidation, you would have the formation of that acid, but this here will not form that acid. If it was an alkene reacting with steam to give you the alcohol that undergoes oxidation, then yes, that would have been the answer. So the answer is C as in cat. Right? C as in cat. All right, number 7. Which diagram shows the structure of pentanoic acid? All right, so 30 seconds, guys. Let me see what you come up with. Which diagram shows the structure of pentanoic acid? All right, so if you just have an OH group, so that means you're dealing with an alcohol. OH group means we're just dealing with an alcohol. So right away, we know that A is not it, and B is not it, because it just have OH groups. We're dealing with an acid, pentanoic acid. Pent is 5, so we're looking for 5 carbons. 1, 2, 3, 4, 5. And it has C double bond O, OH. So we know we're dealing with pentanoic acid. The answer is D as in dog, guys. D as in dog. C is incorrect because it does not have that functional group. What it have here is a double bond. All right, 1, 2, 3, 4, 1, 2, 3, 4. So yeah, this is an alkene. There's a double bond attached to it. So this is not it. So that leaves us with D as in dog. So yes, D is the answer. All right. So question 8. 3 types of organic compounds are alkanes, alkenes, and alcohols. Which structure does not belong to any of these 3 types of compounds? Which structure does not belong to any of these 3 types of compounds? So the answer to this one, 30 seconds, guys. Which of these structures is not an alkene, not an alkene, or not an alcohol? All right, so one person say A. Any other answers? All right, so let's see what the answer is. A has a double bond, so that means A is an alkene. So A can be our answer. B has single bonds. B is an alkane. So B cannot be our answer. D has an OH group. So D is an alcohol. So D cannot be our answer. C has C double bond O, OH, which is the functional group for acid. As the functional group for an acid. They ask which structure does not belong to these 3 listed above. This is the only one that don't belong to those listed above. So our answer is C as in cat. Yes, C as in cat is our answer. All right, question 9. Which structure shows a carboxylic acid? All right, talk to me, guys. What do you think the structure would be that would show a carboxylic acid? Somebody say D as in dog. Remember the formula when the functional group of an acid is C double bond O, OH. So you're looking for that structure. So D as in dog is not the answer. One more try. C as in cat. So the new answer is C as in cat. Let's see if that has it. C double bond O, OH. Yes, that has the functional group. That is our answer. The answer is C as in cat. All right. Question 10. The table shows bonds that are present and bonds that are not present in compound X. So compound X does not have a carbon-carbon double bond. It have carbon-carbon single bonds, so it have single bonds. It have carbon-hydrogen bonds, so it have a hydrogen added to it. It have carbon-oxygen bonds, so it have C double bond O. It have a carbon-oxygen bond. It have oxygen-hydrogen bond. It have oxygen hydrogen bond. Okay, so they ask you now, what type of compound is compound X? So most likely if I have a carbon oxygen bond and I have an oxygen hydrogen bond, it means to say, all right, I have that functional group which takes care of these two bonds here, and I have a carbon oxygen bond that's there as well, so that's taken care of. Carbon hydrogen, so I could put a carbon bonded to hydrogen, okay, and have a carbon carbon bond. So yes, so I'm dealing with a carboxylic acid. The answer is A, as in apple. All right, the answer is A, as in apple. I don't have the carbon double bond, but I have the carbon oxygen double bond and as well as the carbon oxygen single bond. The only way for me to have that is C double bond O, O. But I also have the oxygen hydrogen bond. So oxygen could also be bonded to hydrogen. Hence I have C double bond O, OH, giving me that acid functional group. The answer to 10 is A, as in apple. All right. So again, the diagram shows a molecule of an organic compound W. Which statement is not correct about W? 30 seconds, guys. Let me see what you come up with. So the first thing you look at, you look here and you see that they have C double bond OOH. So that means we're dealing with an acid. Acids have a pH that is less than 7, right? So it's below 7. So you can have pH 1 to 6, right? Not 7. So therefore, a solution of W in water has a pH greater than 7. Okay, so right here, we know that this here is the wrong thing. That should have been, instead of greater than, that should be less than 7, not greater than 7. A solution of W in water reacts with sodium hydroxide. Yes, it would. When copper 2 carbonate is added to a solution of W in water, a gas is produced. Yes, the carbon dioxide gas, because the carbonate is formed. When magnesium is added to a solution of W in water, a gas is produced. Yes, magnesium is added to it. Magnesium plus an acid, hydrogen gas is produced for this one. So the answer is A, as in apple. A is not correct. Question 2. Ethene forms an addition polymer as shown below. Question 2. Which term describes this polymer? All right, so you've seen this question before. I brought it back. Let me see who remembers what the answer is. Talk to me. B as in boy. Yes, that is correct. The answer is B, a saturated compound called polyethylene. So yes, I brought back that question. Okay, so which row describes the formation of a polymer? Which row describes the formation of a polymer? So bear in mind the question that we just did. Let's look at this question and let me see if you come up with the answer. All right, so somebody says C as in cat. All right, so I'm going to take you back to the previous question before we come back to this question. And in this question here, we said that B was the answer, right? So it means to say that ethene formed an addition polymer. So this here would have been ethene. This here is ethene, right? And ethene is forming an addition polymer. And what is formed on this side is polyethene. So polyethene is formed, and it is formed from ethene. All right, so let's go back forward to the question that we are doing now. Which row describes the formation of a polymer? They give us ethane and polyethane, so we know that that's wrong. They give us ethane and polyethene. That's wrong. It should be ethene giving us polyethene. They give us ethene and polyethane. That's wrong. It should be the alkene. They give us ethene and polyethene. So the answer should be D as in dog. All right, question 4. The diagram shows 3 repeated units in the structure of an addition polymer. 3 repeated units in the structure of an addition polymer. So let me try to find the 3 units for you so you can see it clearly. So you have this here is the first unit. This here should be our second unit. And this here should be our third unit. All right. Which alkene monomer is used to make this polymer? It is an addition polymer, so that means a double bond was broken. It is an addition polymer, so that means a double bond was broken. So we take one of these structures and we're going to add back the double bond to it. So it's not A because A only have single bonds. It's not B, B only have single bonds. So we're looking for a structure that has 3 hydrogens and 1 chlorine on it with a double bond. 3 hydrogens, 1 chlorine with a double bond in the center. Right? This here have 2 chlorines. So it means to say they would have changed the structure if they had done this. That is incorrect. So the answer for this question should be C, as in cat. Next question. Which process does not produce carbon dioxide? Which process does not produce carbon dioxide? Combustion of methane produces carbon dioxide. Fermentation of sugar produces carbon dioxide. When we respire, it produces carbon dioxide. So polymerization of ethene does not produce carbon dioxide. The answer is C as in cat. This is the one that does not produce carbon dioxide. C as in cat. All right, question 6. A macromolecule is a very large molecule. The word macro means large. A macromolecule is a very large molecule. Macromolecules can be made by joining smaller molecules together, and this is called polymerization. Which row in the table describes the formation of a polymer? So this is the same question I asked you, except the wording of it is different. What is the answer that you're going to come up with? 30 seconds, guys. All right, so let's do a process of elimination. The monomer needs to be an alkene in order for this to work. So we're looking for something that has a monomer as an alkene. Alkene is out, so A is out and C is out. So that leaves us with B as a possible answer and D as a possible answer. So B, you have ethene, and it gives us polyethene, and that is the correct answer. B as in boy, yes, that is the correct answer. But if the monomer is ethene, it cannot give us polyethane because it's supposed to take the name of the alkene, which is the ethene. Right? That's supposed to take the name of the alkene, which is the ethene. So the answer is B as in boy. All right. So next question. There are two types of polymerization: addition polymerization and condensation polymerization. Explain the difference between these two types of polymers or polymerization. Right, with addition polymerization, the polymer is the only product that is formed. With addition polymerization, the bond is broken and the double bond of the alkene is broken, and that polymer that is formed is the only product. With condensation polymerization, normally a small molecule other than the polymer is also formed. So you normally get the polymer plus water, or the polymer plus HCl, or the polymer and something else, right? In condensation polymerization, the polymer plus a byproduct is formed as well. Part B. Some plastics formed by polymerization are non-biodegradable. Some plastics formed by polymerization are non-biodegradable. So describe two pollution problems that are caused by non-biodegradable plastics. Describe two pollution problems that are caused by non-biodegradable plastics. All right, so non-biodegradable means it cannot be broken down by the environment naturally, meaning to say fungi and bacteria cannot break it down, and plastic persists in the environment. So if animals consume it, then we have a problem. How can animals consume it? When the plastics is thrown into the ocean, right? The fish they mistake it for food and they try to eat it, which then blocks their digestive system, making it difficult for them to consume other food, and then they die from starvation. Right? Animals can be caught in the plastic. So many times, if you look on Facebook and on YouTube and stuff like that, you find that many people are trying to rescue animals that are caught in fishing lines and fishing nets and old plastic bags and all kind of stuff that have been left in the ocean. So if the animals are caught by the plastic, that again could result in problems for us in the world, in Trinidad, in Tobago, in other countries. It would become a problem for all of us, right? When combustion takes place, too much toxins are released into the environment. So we can't just say, well, burn the plastic and that would help get rid of it. Too much toxic gases would be produced, and that would be a different problem that we'd have to try to solve. So we can't just burn the plastic just like that. We need to find a way in which we can get rid of the plastic and get rid of it nice and safely. Right? And the next thing, landfill uses natural resources. We can't just simply go and throw it in the landfill. We can't say, well, let me just throw the plastic in Beaton. It will persist and remain inside of our landfills. And that is a problem again. So they ask you to describe two pollution problems that is caused by non-biodegradable plastics. Any of those will suffice. So the polymer known as PVA is used in paints and adhesives. Its structural formula is shown below. Now, if you look at its structure, let's break it up. They have 1 unit of this, and then they have a second unit of that. Right? So this unit is being repeated over and over and over. They ask you to deduce the structural formula of its monomer. The structural formula of its monomer is this same unit with a double bond present. So the double bond here would have been broken. So this should be CH2 double bond C H O CO CH3, which is the same thing that they have here, except with a double bond. And this is the unit that is being repeated over and over and over. So it would have, they would have gotten it from this here, where this bond would have been broken, right? And instead of having just a single bond, we put back the double bond, and that will help us get back the monomer that was used to form this polymer up here. All right, I'm going back again. I have, if I look closely, I will see that this is the unit that is being repeated. That unit is being repeated because you have CH2, CHO, CO, CH3. Look, the same unit again here. CH2, CHO, CO, CH3. So it's the same thing being repeated. So therefore, it means to say that a double bond was missing from there, right? Because the only way that this unit would be repeated is if the bond was broken, right? The bond was broken before that for this unit to be repeated over and over and over, right? Instead of putting COCH3, I could have just replaced this with R. So you know that as the rest of the group. So if I were to simplify it, it would have been CH2 double bond CH OR. And that makes it look a lot easier. So when the unit is repeated now, you have C, H, H, C, H, O, R. And that's the unit that is being repeated. And you have C, H, 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 and then you have O and R. So the unit is being repeated each time. The unit is being repeated over and over and over. All right, so a condensation polymer can be made from the following monomers. So you have one monomer here, and you have a next monomer there. Then you draw the structural formula of this polymer. So if you look good, you have C double bond OOH here, and you have C double bond OOH there. So this means to say that we're dealing with a diacid. We're dealing with a diacid. On the next side here, we have NH2 and NH2. So we dealing with a diamide, because NH2 is the amine group. So we have a diamide. So they ask you to draw the structural formula of this polymer. Draw the structural formula of this polymer. So if I, let me clear that. All right, so if I remove the OH from this structure and hydrogen from this structure, water is being removed. H, H, and O. Oxygen, hydrogen, and hydrogen is being removed. H2O is being removed. So if that happens, then the rest of the structure could look something like this. So I have CO. Let me clear and do that. CO. Then I have a CH2 group by 4. So I'm just going to call this my R group. CO. I have an R group here. And then I have another carbon here, C. Bond O. And that would be The OH is removed. So let me erase this O here. And then from this structure here, hydrogen is lost. So I'll have NH because the next hydrogen is lost. And I have that group in the middle there, which is CH26. And then that is bonded to NH2. Right, but to make it look a little better on this side, I'm going to replace that R group with a box so you can see it happening on both sides. So you have C double bond O, then you have that R group that is bonded to CO. And this here is the structure that is being repeated over and over. Hence they have CO, CH24. So this here is what I would have put in the box. All right, then C double bond O and H. This here is the linkage that we're looking for. And then I have this here, which is my next R group. And I have the NH on the side there. So what is the functional group that I'm looking for? C double bond O N H. And this functional group here is a peptide bond or peptide linkage, right? That's a peptide linkage. Now, in order for this to make sense, that means you'd have had to go through the lecture that I would have done for the last session for this to make sense, right? Synthetic polymers are disposed of in landfill sites and by burning. Describe two problems caused by the disposal of synthetic polymers in landfill sites. Right now, the problem, we have a shortage of landfill sites, right, especially in Trinidad and Tobago. So it makes it difficult for us to find a place to dispose of them. Right. The next thing, it produces a lot of litter, and it is visual pollution because of it. And also, it's a danger to wildlife. Animals mistake it for food. All right. Describe one problem caused by burning synthetic polymers. With respect to burning synthetic polymers, it results in the production of toxic gases being released into the atmosphere, greenhouse gases being released into the atmosphere, and that is something that we want to try to reduce as much as possible. All right, state two uses of synthetic polymers. Synthetic polymers, we could use it for bags. Now, the word synthetic means to make or to generate, right? So these are polymers that man would make. We use it to make plastic bags. We use it for clothing. We use it for packaging. We use it to make bowls and to make plastic cups and plastic plates. And we use it in floorings and in carpets and in the PVC pipes and insulation and non-stick coating for cooking pans and in roofs and stuff like that. So the structural formula of two synthetic polymers are given below. All right, we have polymer A and we have polymer B. They asked you to draw the structural formula of the monomer of polymer A. So if this is polymer A here, we look for what is being repeated. So we have CH2, CH, CH3, CH2, CH, CH3. So right here, this here is the structure that is being repeated. That is being repeated. So what we do, we're going to put back a double bond right there. So the structure that we'll end up with is CH2 double bond CH CH3. So this here is the monomer that was used to produce this polymer up here, right? A double bond is placed back here. Right? Identify the functional group circled in polymer B. So the function C double bond OO, this functional group C double bond OO, which is also here and here and here, this double bond OO, this is the functional group of a ester, the functional group of a ester. So deduce the two types of organic compounds which have reacted to form a polymer B. The two types of organic compounds which would have reacted to form polymer B, which has an ester linkage. In order for us to get an ester, an acid plus an alcohol gives us an ester. An acid plus an alcohol gives us an ester. Right? So the two organic compounds that would have reacted would have been the alcohol plus the acid. All right, next question. Explain the difference between addition and condensation polymers. Classify A and B as either addition or condensation polymers. So addition polymers, only the polymer is the product that is produced. The double bond is broken and we get the product. Condensation polymers, there is another product that is produced besides the polymer. So, right, most likely it's a simple molecule like water, hydrogen chloride is produced in addition to the polymer. So let's go back and take a look. So this here is one, and then this here is the next one. And they ask you to classify these two polymers as whether it will be an addition polymer or condensation polymer. Now, in order for us to get this ester linkage, it means to say water would have been lost. Hydrogen would have been lost from this structure here, and an OH would have been lost from the next structure there. So H2O would have been lost from the structure in total. So this polymer B most likely is a condensation polymer, while structure A is an addition polymer. Structure A is an addition polymer. So let's go back to the question. Yes, so polymer A is an addition polymer because it would have come from the alkene, while polymer B, two different monomers would have come together to give us the polymer. All right, so question 3. Glucose, sucrose, and starch are all carbohydrates. Their formulas are given below. So you have glucose C6H12O6, sucrose C12H22O11, and starch C6H10O5 in brackets N, because that unit is being repeated over and over. Identify two common features in the formula of these carbohydrates. So the first thing you can recognize is what's obvious. They all have carbons, hydrogens, and oxygens. They all contain carbon, hydrogen, and oxygen alone. All right, that's the first thing we could recognize. The next thing, the hydrogen and oxygen are in a 2-to-1 ratio. The hydrogen and the oxygen are in a 2-to-1 ratio. So I have 12 hydrogens, I have 6 oxygens. I have 22 hydrogens, I have 11 oxygens. I have 10 hydrogens, I have 5 oxygens. So every time I have 2 hydrogens, I have 1 oxygen. So they are all in a 2-to-1 ratio, right? Which is the same ratio as water. So draw the structure of a complex carbohydrate, such as starch. The formula of glucose can be represented by this below. And they ask you to include 3 glucose units in the structure. So from this monomer, hydrogen is going to be removed, and OH from the next structure is also going to be removed. Right? And as it is removed, what that's going to give us is one of these structures binding to another of these structures. Every time hydrogen is given up, and I would have repeated units like that. I have repeated units like that. So they ask us to include 3 glucose units. This is 1, 2, 3 glucose units with 1, 2, 3 linkages that are linking these units together. Box out to the end. And this is our repeated structure. Right? This here is the repeated structure. All right, so next part of the question. Starch hydrolyzes to glucose in the presence of the enzyme amylase. Question, what is meant by the term enzyme? An enzyme is a catalyst or a biological protein, right? An enzyme is a catalyst that speeds up or alters the rate of a reaction. An enzyme is a protein. An enzyme speeds up a reaction, alters a reaction, but does not take part in the reaction itself, right? The enzyme alters the reaction, but does not take part in the reaction itself. Next question. The effect of temperature on this reaction can be studied by the experiment shown below. Starch and iodine form a blue-black color. Glucose and iodine do not form a blue-black color. Okay, so the experiment is set up as in the diagram, and the time measured for the mixture to change from blue to black to colorless is shown. The experiment is repeated at different temperatures. Typical results of this experiment are given in the table below. Okay, so the experiment, we have A, B, and C. The temperatures, you have 20 degrees Celsius, 40 degrees Celsius, and 70 degrees Celsius. Time taken for the blue-black color to disappear, you have 30, 15, and it remains blue-black. So put the experiment in order of reaction rate from the slowest first to the fastest. So which one would take the most amount of time? This one that remained blue-black has not changed, so that would take the most amount of time. So C comes first. Then this one takes 30 minutes. A comes second. And then this one takes 15 minutes. B comes third. So in order of slowest to fastest would be C, A, B. C, A, B. All right. So explain why the reaction rate in experiments A and B are different. Why the reaction rates in experiments A and B are different. So let's go back to experiment A and B. A, the rate at 20 degrees Celsius, it took 30 minutes, but at B, at 40 degrees Celsius, it took 15 minutes. It took 15 minutes. All right, so let's go back. Good. So at a higher temperature, particles have more energy, right? Because they have more energy, they are able to move faster. the collision frequency is greater at a higher temperature. It means to say that there are more collisions at a higher temperature than if it was at a lower temperature, right? So there are more collisions, they collide more frequently, and this increase in collisions increases the rate at which the particles interact with each other, thereby speeding up the rate of the reaction. Right? And the next one is the collision energy. More molecules have enough energy to react from reactants and result in products. That is to say, the energy they have is more than the activation energy, right? And when we go into energetics, we will understand activation energy and having enough energy to convert from reactants to products, right? But simply put simple, higher temperatures means more energy is available, the particles can move faster. A greater collision frequency means there are more collisions, so there are more chances of the right reactants reacting together and producing a product. And the collision energy, they have sufficient energy to change from reactants to become products. So just why the color remained blue-black in experiment C. Let's go back to experiment C. The temperature is 70 degrees Celsius. So most likely that enzyme was denatured, right? Or destroyed. The enzyme was denatured. It lost its ability to function. So C rates was 0. The enzyme was denatured. Yes? When we say an enzyme is denatured, now we cannot kill the enzyme because the enzyme, technically speaking, is not alive. So we can't say the enzyme died, right? However, we can say that the enzyme was denatured because it lost its ability to function. All right, question 4. Polymers are made by the polymerization of simple molecules called monomers. The structural formula of a polymer is given below. So they show you what a polymer repeated unit looks like. This polymer is made by addition polymerization. It means to say that a double bond was broken somewhere, most likely right here. Draw the structural formula of its monomer. So it's this same structure being repeated except with the presence of a double bond right there. So we would have CH to CH3, double bond CH to CH3. Right? And this is the unit that was that we got this repeated unit from. Right? When we're dealing with addition polymerization, it means to say a double bond was broken and the unit was repeated. Right? So this, you could write it out like this, or you could actually draw it out like I drew it out just now to get the actual structure. Next question. The two monomers shown below form a nylon, which is a condensation polymer. So you have your first monomer here, and you have the second monomer there, right? So what can we decipher from these monomers? It have a NH2 group and a NH2 group. So it's a diamide. You have a C double bond OOH and you have C double bond OOH. What is going to happen to them? One hydrogen is going to be lost from the NH2 group and the OH can be lost from the acid group. Right? When that happens, all we would be left with is NH and C double bond O. They can now come and bind together to give us C double bond O and H. That is a peptide That is a peptide bond. So they tell you, name the natural macromolecule which contains the same linkage as nylon. This peptide is found in proteins, and if this peptide unit is repeated, it becomes a polypeptide. Polypeptides link amino acids together. So amino acids together forms a peptide chain. That peptide, many peptide chains together forms a polypeptide, and that helps to form our protein. So what is the name of the macromolecule which contains the same linkage as you would also find in nylon? The name is protein, or a polypeptide, or a polyamide if you wanted to call it that. But we'll explain the difference between addition polymerization and condensation polymerization. Again, addition polymerization, only the polymer is produced from the monomer. Only the polymer is produced from the monomer. With condensation polymerization, the polymer is produced along with another molecule. Most times it's either water or hydrochloric acid, right? With addition polymerization, the double bond inside of the monomer, which is most times an alkene, that double bond is going to break, and all we will have forming is the polymer. With condensation polymerization, a molecule is removed, and thereby producing the polymer that we want, as well as a small molecule. Next question. Many polymers are non-biodegradable. Explain the term non-biodegradable. All right, now the word non-biodegradable, it simply tells us that it does not break down by microbes, fungi, or bacteria. It cannot be broken down by a living organism, right? It cannot be broken down by living organisms. So bacteria and fungi cannot break it down. So they will remain in the environment. So when we say polymer is non-biodegradable, we cannot put it into the soil and let microorganisms act on it to break it down. Like you would do when someone dies, you put their body back into the earth and microorganisms break it down. Part 2. State 3 problems caused by the disposal of non-biodegradable polymers. Well, it results in pollution, one, right? Because you have a lot of plastics that's found on our oceans and our beaches, and it clogs our drains. It results in flooding. Our landfills are becoming filled up, and we running out of space to store it, which becomes our next problem. It is a danger to wildlife and animals, including marine life form, which is in the ocean. If we try to burn it to get rid of it, it results in the release of toxic gases into the environment, which poses a new problem or a new threat to mankind. And there's also a buildup in the amount of greenhouse gases that are present. And this, of course, affects global warming. Part C. Storage tanks for cold water are now made from polymers because they are cheaper than metal tanks. Suggest 2 other advantages of making cold water tanks from polymers. Well, they are resistant to corrosion, so they don't corrode very easily. They are relatively unreactive to water, so you wouldn't have to worry about getting metal in your water. And they are durable. They last a very long time as well. They are light. You could transport a plastic tank very easily once it's empty, right? And they are less dense than your metal tank. It's easy to make and manufacture. It can be molded and shaped into any shape that you want it to be. And they are good insulators, which means to say that it keeps the water cool. Next question. Many monomer molecules react together to form one molecule of a polymer. This reaction is called polymerization. This reaction is called polymerization. The structural formula of the polymer polychloroethene is given below. This polymer is known as PVC. So they show you what the unit that is repeated is, which is CHHCHCl, and that unit is repeated however many times. Part 1. A major use of PVC is insulation of electrical cables. PVC is a poor conductor of electricity. Suggest another property which makes it suitable for this. It does not decompose very easily. It's non-biodegradable. It's very flexible. It can bend. It can be easily molded or shaped. It has a low density. It's light. It's lightweight. It's waterproof. It's insoluble to water. It does not corrode very easily. Any of those things would be correct, right? Because they're asking you what are the properties of PVC, right? So just think logically. That's the reason why they could use PVC to allow water to run through it, because it does not corrode very easily, which makes a lot of sense. Part 2. One way of disposing of waste PVC is by burning it. This method has the disadvantage that poisonous gases are formed. So just two poisonous gases which could be formed by the combustion of PVC. You could have the formation of carbon monoxide, you could have hydrogen chloride gas, you could have chlorine gas. They can all be very dangerous in high concentrations. Part B. Deduce the structural formula of the monomer that is formed from this. Deduce the structural formula of the monomer that is formed from the polymer given below. So they're asking you what is the formula for the monomer of this structure. A double bond was broken. So this should be C double bond CH CH3. And then over here, of course, I'll have HH. All right, so this here is what you'll get, which is CH3, CH, which is CH, and then double bond CH2, double bonded to CH2. Right? In essence, it's the same thing I drew back, except I added back the double bond inside of there. All right, deduce the structural formula of the polymer polyphenylethene from the formula of its monomer phenylethene. So if you look at it, there's a double bond present. If I'm trying to get the polymer, this double bond is going to be broken, and the bonds will be added on the side there. So I'll end up with C, H, C6, H5, single bonded to C, H2, and this unit is now going to be repeated for n number of times. All right, which is the same thing that they have here. You could either write it out like this, or you could draw it out as I draw it out. Either way is correct. Next question. The carbohydrate glucose polymerizes to form the more complex carbohydrate, starch. If glucose is represented by HO with this box OH, then the structural formula of starch is as drawn below, and they draw the structure for you. How does the polymerization of glucose differ from that of an alkene, such as phenylethene? Now, glucose, 2 units of it produces a polymer and water, right? This happens via a condensation reaction. So we have condensation polymerization taking place here because the water is being removed. However, with phenylethylene, one product is formed, and that's from an addition polymer. So if I go back to the previous question, this here is phenylethene, and all that happened, the bond broke, and we had the polymer being formed. And this polymer, this is the only product that was formed. However, with this structure, water is being removed, right? So if I were to put 2 of these structures next to each other, water is going to be removed. So this type of reaction is a condensation reaction because water is being removed in this one. So I'll have 2 products, the polymer that is produced as well as a side product, which is water. So this here is condensation polymerization, while with phenylethene, it's addition polymerization. Next question. Domestic rubbish is disposed of in landfill sites. Rubbish could include the following items. And they have the items, they have newspaper, cotton rag, wooden glove, aluminum container, styrofoam, and then they show you how long it takes for these different products to break down in the natural environment. And the question is, explain why aluminum, a reactive metal, takes so long to corrode. And it's simple. Aluminum reacts with oxygen in the air to form an oxide layer that is a protective layer for the aluminum. And it's because of that, aluminum takes a very long time to break down. Part B, both paper and cotton are complex carbohydrates. They can be hydrolyzed to simple sugars such as glucose. The formula of glucose can be represented by this formula below here. Draw the structural formula of a complex carbohydrate such as cotton. Include at least 2 glucose units. So basically this unit here is going to have repeated units of it. So I have HOH bonded to our next one like itself. And again, what's going to happen? Water is going to be removed, hydrogen from that one, and OH from this one. And then this comes and binds there, and I have one structure bonded by oxygen to another structure, which is bonded by oxygen, to a 3rd structure, which is bonded by oxygen, to a 4th structure, and it is repeated over and over and over. All right. So next question. Wool is a protein. It can be hydrolyzed to a mixture of monomers by enzymes. Part 1. What are enzymes? Like I said before, enzymes are catalysts, or enzymes are proteins, right? Basically what they do, they speed up or alter the rate of the reaction that is taking place. Part 2, name another substance which can hydrolyze proteins, a strong acid or a strong alkali, right? Hydrochloric acid or strong alkali, sodium hydroxide, they can hydrolyze proteins. What type of compounds are the monomers formed by the hydrolysis of proteins? When proteins are hydrolyzed, now hydrolysis is the splitting by, right? Lysis means to split. So what is happening when we split or we break up a protein, we form the basic building blocks of the proteins, which are amino acids. What technique could be used to identify the individual monomers in the mixture? You could use chromatography, right? And that's something we'll get to when we talk about the different types of tests that we do in chemistry. Part 5, proteins contain the amide linkage, right? And just to remind you, C double bond O and H is our amide linkage. Proteins contain that amide linkage. They say name a synthetic macromolecule which contains the same linkage as that. Nylon and Kevlar, they all contain this same linkage, this amide. The amide linkage, C double bond O and H. What is the scientific term used to describe polymers which do not break down in landfill sites? And the name is non-biodegradable, right? When things do not break down naturally, we refer to them as being non-biodegradable. Styrofoam is polyphenylethene. It is an addition polymer. Its structural formula is given below. They ask you to deduce the structural formula of the monomer phenylethene, right? The monomer is phenylethene. How are we going to get back the ethene? It would have come from the alkene, so therefore a double bond should have been here. The double bond was broken in order to form this structure, so therefore we put back the double bond and rewrite the structure, and that will give us the monomer which was used to produce this polymer. All right, so plastics are polymers. They are formed from their monomers by polymerization. Two methods for the disposal of waste plastics are burning and recycling. Describe one advantage and one disadvantage of each method. I've put in a couple, right? With burning, it produces toxic gases that are harmful to your health. Increases greenhouse gases. It results in global warming. Reduces visual pollution, right? Which is an advantage, but it also reduces litter that you could visibly see. It reduces the risk to wildlife because you burn it. There's a shortage of landfill sites, which is a negative. Reduces the space needed in landfill sites, so it saves space, which is an advantage. Non-biodegradable, which is a disadvantage. It takes a long time to rot, so if you burn it, then that's an advantage. It takes a long time to decompose, which is a disadvantage. It accumulates a lot of waste, which is a disadvantage. We can use it as a burning source of energy, which is an advantage, and it could use to generate electricity from burning, which is an advantage. Recycling, conserve petroleum, meaning we save on oil, natural resources. But the problem is it's difficult to recycle plastic, right? It's expensive and it takes a lot of energy to recycle plastic. The problem comes from sorting the plastic. It reduces the need for a landfill if you recycle though, which is an advantage. And the quantity of plastic that is reduced each time it is recycled, the quantity is reduced because we are using over and over, we're using some plastics. Instead of producing the same amount, some can be recycled, so there's less plastic buildup in the environment. All right, now you don't have to put all that I've written down there, right? You could only put the ones that applied, put two, one advantage and one disadvantage, because that's all they ask for, one advantage and one disadvantage. Purpose of putting the others, in case one that I had said crossed your mind and I did not put that down as the answer, you could consider the others as well. And other related answers would be also be correct. All right. So there are two types of polymerization reactions. Give their names and explain the difference between them. Okay, so this question we've come across a couple of times. So now addition polymerization is one and condensation polymerization is another. With addition polymerization, only one product is produced. There are no byproducts, right? Just the polymer is produced. With condensation polymerization, the polymer is produced as well as a byproduct. So the byproduct most times is either water, hydrogen chloride, or another product is formed. Question, give the structural formula of a polymer which is formed from two different monomers. Right now, that can happen for a polyester and it will also happen for a polyamide. Right, so this is the structural formula of a polymer which is formed from two different monomers. It could happen for a polyester, because esters are formed by the acid and an alcohol reacting together. It forms a ester. So if we have a polyester, it means we have repeated units of acids and alcohols coming together. With the amide, again, it's an acid reacting with an amine group. So we end up with a polyamide being formed. And let me take you to the next page. Yes, so this here is our dicarboxylic acid. The acid is reacting with the alcohol, and that is what is giving us our ester. Because we have plenty units of it, it's a polyester that is formed. Again, water is removed here. OH and H, water is removed, and then this structure comes and binds right there. So I end up with C double bond O with the box C double bond O, and this here comes and fits in right there nicely. Again, the hydrogen of this would be lost to the OH group from this side of the next one is going to be lost again, and that unit is repeated over and over and over. All right, so that's our polyester from two different monomers. And then we have our carboxylic acid. All right, this here, this is a dicarboxylic acid. Why? Because I have C double bond O, OH and C double bond O, OH on one side. On the next side, I have the diamine. I have one amine group on this side, one amine group on that side. What's going to happen is that the OH from this group here is going to be removed. Hydrogen is going to be removed from this structure. And this, what remains here will be one hydrogen. It comes and it binds. So I end up with C double bond O, NH, to give me this peptide linkage. And I have the formation of what is called a polypeptide or a polyamide, right? And it would have been formed from two different monomers, a diamine and a dicarboxylic acid. All right, I'm coming to the end of the lecture that I'm giving today. All right, there's just a couple of things I wanted to show you. All right, I want you to talk about saponification because I spoke about it in one of the questions earlier. So I have a short video for you to listen to.
What is soap? Have you ever thought about what soap is? The slippery, sudsy stuff we use every day does its job without us thinking much about it. We know it makes the world cleaner, but do you know what makes soap soap?
I have no idea. I'm pretty sure that some plants might make soap. Well, it has animal fat and chemicals in it, and maybe some oil, some perfume, some bubbles.
Good guesses. But the secrets of soap are much more interesting than that. Most soaps we use today are mixtures of ingredients people have been experimenting with for 5,000 years. Let's take a look at the ingredients we use to make soap today. First, and most importantly, are surfactants. These are the chemicals in soap that remove germs and dirt. Surfactants attach to germs, dirt, and to water. Surfactants hold onto the germs and dirt as the water washes them away. Then there's fragrance. Fragrance is added to cover the odors of ingredients that might not smell so great, or add a pleasant scent. Preservatives are added to keep microscopic bugs from growing and eating the soap ingredients. A pH adjuster raises or lowers the pH of a solution, making it either more acidic or more basic. The pH level affects how well the soap does its job. Depending on the type of soap, there are many other chemicals that can be added. These include dyes for color, thickeners to help keep the soap from running off your hands, moisturizers to soften your skin, foam enhancers to create more suds, builders to provide surfactants with extra cleaning power, and antimicrobial ingredients to kill microorganisms on your skin or body, including the ones that cause BO. Last but not least are solvents. These help to blend the ingredients and give soap the right consistency so it's easy for you to use. Creative people like you are working to improve soap every day. And since it's so important to everyday living, this work will go on forever. If you're interested in chemistry, toxicology, or protecting the environment, there are great opportunities out there for you in the world of soap. It takes creative people to make soap, now and in the future. Check out our website for more information.
Okay, so I have a next thing I want you to see.
We are going to learn about how soap is made by a process called hydrolysis, and how we can control whether the soap produced is hard or soft. Soap is a detergent and has been around for thousands of years. Traditionally, ash from wood fires acted on animal fat in the first soap-making processes. When animals were baked on a spit over a wood fire, the fat would drop onto the ashes. The ash contained potassium carbonate, which broke apart the fats, and so the ashes, when wetted, were excellent as a cleaning agent for the pots and pans. Soap is a substance that, when used with water, removes dirt and oil away from the skin or other materials such as clothing. Soaps have always been made in a similar way, using hydrolysis. The fancy word for this process is saponification. Chemically, fatty acids or oils combine with a base, typically sodium hydroxide and water. The result of this process is soap and a chemical called glycerine. This is seen in the chemical reaction where the fatty ester highlighted is broken down to form a carboxylate salt and glycerin. Glycerin is found in luxury soaps because of its ability to make soaps appear translucent. There are two kinds of soap, hard soap and soft soap. What do you think this means? Pause the video and continue when ready. Soaps can be hard, meaning they can be moulded into shapes, typically a bar, or they can be soft, like those found in hand washers, which are liquefied and kept in bottles. In addition, hard soaps dissolve more slowly, whereas soft soaps dissolve more quickly. Hard soaps are made by using certain fats, like coconut oils, lard, or cocoa butter. Look at the equation shown now. The R group represents the size of a hydrocarbon chain. How do you think this might influence whether a soap is hard or soft? Pause the video and resume when ready. The R groups of a particular length alters the fat's properties, particularly its melting point and its solubility. In addition, the choice of base, such as whether you use sodium hydroxide or potassium hydroxide, is also important. Typically, hard soaps are made when fatty acid esters with R groups containing 12 carbons or more use sodium hydroxide in the saponification process. Fatty acid esters with 6 carbons or less are not used as they irritate the skin and smell pretty funny. Soft soaps use fatty acid esters like avocado oil, sunflower oil, and castor oil to name a few, and are reacted with potassium hydroxide when saponified. In summary, soaps are made by a process called saponification. Really, this is a hydrolysis reaction, whereby a fatty acid ester bond is broken and a carboxylate salt and glycerin are formed. That carboxylate salt is the soap that we use when we wash, and can be hard, as in a bar of soap, or soft, like that found in a hand wash.